就是
那一会儿直接站在那怎么办？
站着不就记了啊？站着看着呢，不就记了？
放着而已。
一周几组？3组。
感觉好吧，看罗嘛。
Are you able to share?
Let me try.
Yeah.
Yeah, it works. Thì phải có một bài post lại.
Okay. More like kind of late. Maybe like 2 minutes. No, so the professor is at a conference. So, my name is one of his PhD students. Then this.
你要介绍名字吗？你要介绍名字。你要介绍名字。
No, I think he's gonna like record a video. I don't know, done that before. He might record like a lesson and then send that to you guys to watch it every time. So yeah, for the time being, I think we'll just do the like 3 or 4 presentations then. And yeah, you guys know the expectations. And any qualms before we start? No? Okay, let's do it.
Go ahead. Today, let's talk about a key tech for keeping software safe. We call this CFI, short for Control Flow Integrated. And I'm Dennis. He's Shen Yi. He's Hugh. He's Yanan. And think of CFI as a security guard. What is its job? Its job is to make sure a program only follows the safe path it is supposed to, and blocking hackers from sneaking in harmful territory, especially from ROP attacks. But making CFI work everywhere is very difficult. Here's why. The first problem is about the access requirement. Imagine you need a special key to put this card in the place. But for many programs, especially the program you bought from the commercial company, that they even give you the source code, which is the special key here. So when you didn't have the source code, you cannot use CFI here. So no source code, no CFI. Then the second problem is about the slow thing down. If CFI were God, it's like one that's super careful, checking everything and everyone. This means things can get up to hot as slow again, which can be a big problem for apps that need to run fast. And the third problem is about security implication of loser CFI notion, right? People try to use loser CFI to make it more practical. Could you guys imagine that when people try to make CFI feel a bit better, some have tried using a lighter guard, not checking as much, but does it still keep the does it still to keep the bad guys out? Maybe not as well as we would hope. And for the most problem is about like the advanced ROP attacks. Seems like our CFI has like the good best version here, but maybe there's the advanced ROP, maybe like the best version of ROP. They will find a place to stick to your program. So we need to consider about this problem. And
yeah. Conventional attacks to CFI include 4 approaches, which are shown in the graph: the code injection, the code reusage, the code banning, and the data pointer corruption. But today we're just only going to focus on the code reusage attacks, especially on the return-oriented programming, like return of function while for loop, and the jump-oriented programming, abbreviated as ROP and GOP as shown. To tackle this problem, CF architect has to have to utilize a method called control flow graph to ensure that every control transfer or control flow transfer is indeed intended by the original program itself. Because the task can introduce some extra random or like overflow pointers to this program to corrupt the control flow integrity. There are many ways to solve this problem. Very simple one is just assigning IDs to every control flow transfer. For example, branching or jumps, if you're familiar with computer architecture. I'll show you the picture. Every function, when calling like a subfunction or like a parent function, will be assigned an ID. And after it returns, it's gonna check the IDs then and go back to the original caller with the parent function. No. As mentioned before, CFI has many drawbacks. For example, this one, it introduces extra like tremendous amount of computation overhead and latency, especially if the program is very short. For example, just like 4 loops every time you have to check the IDs, and maybe just a simple multiplication, you might have to check it again. Also, as mentioned before, this method requires a full picture of how this control flow works. Like at this moment, what is happening? Maybe at that moment, like you have to call your parent function or so. So it is not really always available to the designers at like design stage, but more likely on ground stage. Yeah. That's why the loser version of CFI was introduced. A very simple loser at CFI was, of course, was just giving all the control flow transfer with the same type. For example, all the branches have the same ID, all the jumps have the same ID, as shown. So like there's not a lot of overhead. For example, you don't have to check ID 41 and you don't have to check ID 2 ID 1. But this like this loser CFI does have similar CFI insurance as the ideal CFI we were introducing before, like the many IDs and like the whole picture one. But it does have some drawbacks. The first drawback is, yeah, clear. It does not have exposure to the most recent invocation of the parent function. For example, it can show in the red, or this function can return to either sort 1 or sort 2 because they all have the same IDs. And the second problem is the loser version of CFI is the ID, because the ID pool is so small, you only have like 2 bits or 3 bits, so maximum like 7 IDs for control flow transfers. Like sometimes the control doesn't go back to the raw one because, for example, like you have all the branchings have the same ID, but what about branch equal or branch greater or branch less than? Finally, CFI does promote higher possibility of over-permissible transfers. And all those weaknesses are gonna be even worse if we run this program on multi-thread and multi-core system. Yeah. To grasp like a better understanding of how exactly attacks land their attacks on CFI, we introduce this concept called gadgets, which are small sequences of a repetitive code that mimic the behavior of ROP and GOP described aforementioned. And in this study, we specifically talk about the EP and CS gadgets, which corrupts the data or corrupts the data usage or the pointer usage at the entry and the return at the entrance and return areas of a control transfer. And like the evaluation will be introduced later from her.
Okay, so I'll introduce the evaluation methodology. So the team took a detailed look at the CFI, checking out different ways, different types, like the first one by body, CCFIR, and being CFI. They wanted to see how CFI works to keep software safe from attackers. So they didn't stop there. So they tested CFI with the real challenge by targeting Internet Explorer 8. They use a heap flow. That's basically a security weakness, and to bypass another defense called ASLR, and to treat CFI itself. So this showed that they could use one weakness to achieve 2 goals. So the main result is that So there's an interesting thing that even with CFI doing its job, the studies show that it's still possible to snake in attackers. So that means CFI isn't totally safe. So when the team look at the popular apps, they found that a lot of like gadgets, like there are small pieces of code that attackers can use, even when the CFI is supposed to block them. So it shows that even good CFI setups have their weak spots that attackers can find and reuse. But the study wasn't just about pointing fingers at the CFI's problems. It also made it clear that we need to think bigger, and when it comes to like protect software. So just to make CFI together isn't enough. We need to like get creative and find a more safe way to fight the attackers. So what's the main takeaway? So the study remains that the CFI where it's strong, but it's not unbeatable. So it's called an action for everyone that's cybersecurity to think about the attacker and come up with a smarter ways to protect our digital world. So there's something we need like work together.
And next, I will show some potential future work about the CFI and machine learning, a very hot and popular technology, and investigating the possibility of integrating it with the CFI mechanism is maybe a possible method to implement a more dynamic and adaptive mechanism. And by analyzing the patterns of anomalous control blow changes, and machine learning modules could add an additional layer of security that could adapt to some emerging threats, and by doing this, it can enhance the security without compromising performance. And the second one is, as mentioned before, the looser notion of CFI will beneficial for the performance. It will leave the system vulnerable to some complex exploits. And a granular method to solve this question is to classify the pointers based on their usage context and the potential future implications. And I think it's a great way to develop neurons, the CFI policies. And instead of dealing with the mechanism directly, as we think we can exploit the hardware optimization, and I think is possible ways to improve the security without influencing in the performance. And by embedding the hardware, the CFI checker into hardware, and we can reduce the overhead associated with the software-based solution. And next. And finally, we will put some discussion points about the CFI and the critical challenge in CFI improvements, and that lies in the utilizing and the guiding the runtime information, and results improving some performance penalties. And then how to bridge the gap between them is need to create some innovative policies. And the second one we want to consider is whether the current methodology to evaluate the defense mechanism is adequate, and whether the current evaluation of CFI mechanism comprehensive for different situations is another interesting thing to discuss. And it's all our presentation. Thank you for your patience and listening.
Any questions? I have a quick question, I think. So did they run this like on any hardware platforms, or?
They set the benchmarks. Yeah. They run, it's not like a very standard benchmark from Like
Oh.
info, test members.
Oh, did you guys show that? I don't know. I don't recall seeing a,
Oh, yeah.
I mean, you didn't have to, but I was just curious if they did.
I think this friend said show minimum detail for results.
Sure.
Okay.
Yeah. Okay. But they ran
Yeah, they
benchmarks.
ran
Okay.
on the.
And what were like the performance overheads
I don't-
of their
I don't
method?
remember. I don't-
Do you remember? Okay. Yeah, I'm curious. Yeah.
You know what, you can read the paper.
Yeah, okay. Yeah, no, you can't pull that on me. Yeah,
That was interesting.
sure. Okay, no more questions? All right, thanks, guys. Thank you. All right, I guess the next group, you guys can get ready.
Students is this.
No.
So there's supposed to be actually like 16 students, but there's a 17 students that they see. So one of them that's it, those things you can figure out who it is before everyone gets to it. Yeah, they're
Hi, everyone. This is our group. We're talking about pointer integrity using ARM pointer authentication. I'm Billy. I'm Subhas. Neil. I'm Parth. So yeah, let's start off with just a little bit of background. I know we've talked a lot about this in the class, but traditionally when we're dealing with like jump-oriented programming or parent-oriented programming, we have a lot of ways to solve this, and notably, willful integrity is a way to make sure that whenever we have any paths that the attacker is trying to make mistakes, we fail the paths if they don't exist in the original program, right? But this isn't the limit of what attack can do. So what attack can also do is, next slide. They can also perform non-controlled data attacks. So example of this is just think of a user identity data. So you try to log in as a user with low permissions, and then suddenly you can corrupt the data pointer that holds the information for the cache information for your user and change that to a user with higher permissions. Suddenly you can access a lot of data that you wouldn't be able to do before, right? So there's still potential for a lot of attacks without going through different control flows in the training program. So what can we do against pointer corruptions? Well, ARM has a feature called pointer identification, where we can create a map for the pointer that's stored inside the pointer itself, called the path here, where we create it with a key, a modifier that's user input, and the virtual address of the pointer. So what do we actually gain from using pointer identification in ARM itself? Well, the checking is done in hardware. So since the map comparison is really in hardware, we get a lot more efficient comparisons than if we need software instructions to help us out. So how this is actually constructed is we store the keys in kernel level permissions. So whenever the attacker has control of user level code, it's not able to see the keys. And we use this by instrumenting the code. Every time we use the pointer, we're going to create a authenticated pointer before usage, and then we're going to authenticate it before usage. So what are some of the attack vectors on these tracks? Well, it is possible that there could be some guessing attacks, but that's not determined as the primary attack vector. So what the primary attack vectors are here is malicious attack generation, which is when the attacker either controls the pointer that's unauthenticated, or it controls the modifier. Both of those gives the attacker a pointer that they know they can use in their attacks, as well as doing reuse, which is if they find a properly authenticated pointer with a non-unique modifier, what they can do is substitute the pointer with something else that has the same modifier, and now you can use a pointer in a place it wasn't used.
So now let's talk about some of the things that the attacker can do and some of the requirements that we have to make sure that we can stop as many attacks as possible. So first of all, the main goal is pointer integrity, which is to try to stop any sort of malicious or non-expected use of the pointers. So for our adversary models, we know that the attacker can first of all read any part of the memory, and that the attacker can write or modify all non-code segments of the memory. Furthermore, address space randomization won't work. So like, even if you mix up the address spaces, the attacker can still know exactly where everything is. So some of the requirements for our system are, well, first of all, pointer integrity, but then we also want to make sure that PA attack resistance is present so that we can reduce as much like reuse attacks and try to stop the attacker from creating their own attacks. And then we also want to make sure that we're backwards compatible, so we want to allow the protection of existing programs without like interfering with their operations. And then finally, we want to do all of this with some reasonable performance costs. So now let's talk a little bit about the main points of our design. So first of all, we want to create some sort of pointer authentication instructions. Now these will be inputted into the program anytime the library, which we'll get into a little bit later on, sees that pointers are loaded, stored, or created. And basically what these do is that they make sure that there's no malicious behavior with the pointers or the data that they're pointing to. Next, we want to, Next, we want to also make sure that we create these packs or pointer authentication codes in pointers or data that isn't runtime allocated. And the way that this is done is that the parts library, which we'll again get into a bit later on, creates custom initializer functions, and then during runtime, packs are created using these custom functions. And then we also want to have pointer compartmentalization to try to reduce as much reuse attacks as possible by having like separate pointers for code and data, and then also by checking or also by having runtime type safety, which is basically where the library will make sure that the pointers can only point to very specific types of data. And then we also want to have return address signing, and this is done by using the stack pointer denums to make sure that the attacker can't reuse return addresses or like authenticated return addresses. And then we also want to have onload data pointer authentication. Now what this basically means is that every time data is loaded into a register, it's authenticated. And then similarly for code, we want to have on-use authentication, which is basically where every time you're about to execute the code, you authenticate and make sure that it is the correct code. And then finally, we want to make sure that if we do want to change the type that the pointer is pointing to, we do this in a secure way by changing the pointer authentication codes for that based off of the type that it's going to.
All right, so in order to solve some issues associated with the security of pointers, and adding on the pointer authentication that aren't provided, the paper created parts, which is pointer authentication assisted runtime safety, and it solves 3 issues. Number 1, it adds signing for code pointers. Number 2, for data pointer signing. Also, number 3, for return address signing. Neil earlier mentioned the issues with return address signing. And this also helps mitigate pointer reuse because it binds the return address to the function definition. So you can't, for example, have the attacker grab a authenticated pointer that was used in one function, take that, hold on to it, and then use it on another function, to get access to something that is not supposed to have access to. Another thing that the paper talks about is hardening return address signing. So they use stack pointers as modifiers. And the point is that you don't want to have a modifier that is static all the time because then it is easy to find, locate, and reuse over and over again. But you also don't want to have a pointer that's or a modifier that's reallocated every single time because it adds too much overhead. So they struck a balance by having stack pointers that change at runtime, and it has the same value from the beginning to the end of that function. But it also has a function ID, like I mentioned earlier, so ID is assigned at compile time, and it prevents the cross function reuse. So here's how they implemented it. They really had a three-part, I guess, on the back end in order to implement this. So first, they have a optimization path at a high level that generates the metadata that's necessary for the pointer authentication modifiers. This is the first pass in the intermediate code representation, and then the second pass, they go down to the hardware level and they have AR64 modifications in order to authenticate the linked register values. And thirdly, they have a backend pass that takes the PA modifiers and then they generate the low-level instructions for the actual.
So when we're trying to analyze the performance of parts, we have kind of two metrics that we wanted to solve. The first being whether it's actually secure, and the second one being that we didn't sacrifice performance. So we can kind of analyze it from both of those regards. So as far as the security improvement goes, it's not as tangible to measure, but we can kind of make sure that all the attack avenues that were identified by the paper are closed up. So the first one is return address signing. By, as Billy mentioned, mangling the stack pointer with the function ID itself, you prevent reuse across different functions that attackers could potentially have access to. So that avenue is closed. Then we also have data pointer signing. So it prevents attackers, at least parts does, prevents attackers from corrupting pointers to take control of the system. And there's also the runtime safety that was introduced where you assign the different IDs at runtime that can help restrict pointer substitution. But that being said, parts also allows for pointer conversion. So if you want to convert a pointer from like A to B, it allows for the implementation of that, which means that while it's converting A to B and creating a new pointer authentication code for B, an attacker can actually intercept it in the middle and potentially gain access to an authenticated pointer that way. So it does unfortunately open up an avenue for attack that is slightly new. Finally, one of the security improvements is also pack entropy. By kind of taking a good enough block size, which is estimated to be between 16 and 24, you were able to prevent guessing attacks with a really high probability. Finally, we also have the performance improvement. I say improvement, but it's mainly just making sure that you aren't sacrificing too much performance at the cost of this. So because you're actually trying to authenticate and sign every single data pointer you use, that's extra instructions, that's extra execution time. So there is a bit of overhead. But when they added a lot of benchmarks to actually test how this code performed, they found that return address signing has a negligible effect because the amount of times you have a return operation is pretty small in the context of larger functions and larger programs as a whole. However, data signing, because that's applied to every single data pointer, did create a much more substantial increase, and they approximated a geometric mean of 19.5%. So you can kind of see in the chart here how like, you know, something like a floating point emulator has a lot of floating point operations, a lot of data pointers, so it has a lot more overhead, while other functions were able to perform slightly more often. So it all kind of balances out to a relatively modest amount. And then finally, we had some discussion questions, some that are more philosophical, like at what point do you want to sacrifice performance for security? And then some that were more specific to the article, such as like how can you use more emerging hardwares to allow for better runtime. But yeah, thank you for listening to our presentation.
No questions? Great presentation. I had I think kind of a simple question. So are they essentially like modifying some pointer integrity routine that like ARM is already providing? Or like so my understanding of this is that ARM kind of provides this like hardware mechanism for this, but they're making modifications at the compiler level. Okay.
That's pretty much it. Like the ARM 64 has pack.ia.
Yeah.
Create the actual like hidden context and then in hardware they do. What this is doing is extending it with the runtime safety, and that's at the compiler level, where basically now you're assigning like type ID 7 and ARM is agnostic to what the actual type of pointer is, the pointer, and then whichever key they use to compare to whether it's like it doesn't care like what it's actually doing.
Yeah.
So now we know which type of points to it, so we know you can't corrupt it.
Sure. Yeah, that makes sense. Okay. That's all I got.
Right.
Cool. Great job, guys. Yeah. I don't know. Have you guys been sending slides?
There's a wide range, like, it's like technical resources.
Okay. So just do that. I don't really know.
Yeah, I do that. Oh,
And then basic note. There's no route. Yes.
All right, so yeah, hi, we're here to present our presentation about the paper introducing dynamic information flow tracking. I'm Nathan, that's how that's David. All right, so yeah, right now we're just gonna contextualize the problem a bit. Okay, so yeah, this paper was this paper was released in 2004, but like with every year, like and especially the rise of like Internet of Things devices, our code bases are becoming like more and more vulnerable every day. Like the more information that we have like introduced in all of these devices, the more vulnerable it is to some of these exploits and the more we can lose. And then this is just like a diagram of like reported losses over the past few years from cybersecurity attacks. And a lot of these vulnerabilities stem from like lower level efficient programming languages such as C. And like a lot of other things, like a lot of other high level languages are like implement protections against these attacks, but due to like efficiency and then time and resources needed to implement these protections, other companies just like skip that. So, so yeah, this is just like a code or a data point I found about like the amount of vulnerabilities that are known and like open source, like people know how to exploit them and companies know about them, but a lot of times just like company resources, time, and then the efficiency loss just makes us just ignore some of these things. And now Dave's gonna get into some specific stuff about C.
Sure, so this is just some of the background. So C is vulnerable because like a lot of the earlier functions implemented in C were naively implemented without taking security into account. And the reason why a lot of code hasn't been migrated to different languages because it's time consuming and it's complex. And also migrating to another like safer language like Java can actually cause like performance dips. So some of the vulnerable functions in C are like the gets function, spread that function, the screen copy function, and these functions actually don't check like balance for like the input size. So these are some of the attacks that can be utilized. So first we have like DX matching, which is also known as buffer overflow. And in this part of code, we're basically copying the input bar into our bar array, and it's not string copy is not checking the length of bar. So That's how we can overflow the char array and overwrite like unintended char array. And this is just like some of the visualization. So with bar, we can overflow with using the A's as padding, and then we can overflow to the return address, and the return address will jump back to the top. Yeah, back to the address over there, and we'll have like malicious code being executed there. And we also have string formatting, which is taking advantage of format specifiers in C to sort of overwrite characters in like a certain memory location. And where you can use this modulus n, which is used to print the number of characters currently like that we've written so far. So in this part of code, you can use this printf function and pass in a modulus n, which allows us to write 4 to the address 0x61, 61, 61, 61, 61, which is basically which is the address A in hex.
Okay, so going on to the solution that they provide in the research paper. So what should we?
It doesn't want to slide up or something. Okay, so yeah, the attacks that we just mentioned, they all depend on like using malicious IO inputs like as part of our program. So the idea behind this paper is to just like track the inputs from like untrusted IO and then see how they're used throughout the program. And then once a value that depends on those malicious inputs is trying to be used, then like check the security. And then that's how we can efficiently like only do security checks when we need it. Slide. And then yeah, and this is just like a general like flow chart from recreated from the paper. So you see the operating system like tags the IOs that are spurious, meaning we don't fully trust them. And then we watch how dependencies values dependent on those values come up throughout the program. And then once they're used for something potentially dangerous, then we check.
Okay, so building off of that, how do we categorize these spurious functions? Slide. The first thing is copy dependency. If you have some spurious information and you copy it to another point, you have to assume that's also spurious. Computational dependency, if you and your arithmetic with spurious information, the result is also spurious. LEA, or load address dependency, is if you're loading from some spurious address, that what is loaded from there is also spurious. And store STA dependency or store address dependency is if you're storing to that address of the spurious pointer, then you can assume whatever was stored there is also spurious. And control dependency is just generally if you're executing any kind of values from spurious values, then anything that was executed is also spurious. So these are the traps that they introduced in the research paper, and it's just how looking at instruction load stores, register jumps, conditional branches, all of those will trigger some type of trap if the security tag says so. Next slide. So how do we efficiently manage these security tags? Next slide. So obviously with a large batch of data, you can assume that most of it will remain authentic for most of the time. So putting a security tag on each byte would be a waste of resources. So what DIFS proposes, or dynamic information flow tracking, is that we should add security tags based on the granularities of the writes. Next slide. So 00 means it's a straight authentic page. It was just made, so why need to allocate memory for any kind of security tags? 01 is quad words. That means anything greater than a quad word, you'll use 01 granularity. 10 is per byte, so less than a quad word, and then 11 is basically saying if you already have written to some kind of page, but then some kind of further value entered that page, the entire page is now further.
All right, so next we'll talk about performance and what were the results in the memory space and what the simulations show us. So the simulations, or how we ran these tests, is we want to evaluate our effective, like our approach of these applications on an x86 architecture. So they use the modified botched architecture for this. So the memory space overhead of the security tags, and here we have the results from their testing. It shows that the security policy only allows a certain amount of spurious data. Over 85% of pages have per page tags, and space overhead is only 1.44% on average. This is really good, and per page tag basis allows fine-grained control and monitoring of access or modifications on a page-by-page basis. Next, even for a tagging policy that generates most spurious tags, the space overhead is less than 3.7% on average, which is really good. Next, we talk about the protection scheme effects, and the two main impacts of this and the diff on the security here is that accessing security tags will consume off-chip bandwidth. Bus bandwidth is polluted by tag accesses, where the average bandwidth pollution is only 2.1%, which is, again, very good. And the assumption about dispatch. Now we assume that the dispatch of an instruction waits until data and tags are ready. Therefore, memory access latency is the max of the data latency and the tag latency. Here are the graphs for performance overheads for the cap sizes, and they tested various L2 cap sizes, and then they also tested it with a 1 megabyte unified L2 cap, which is shown down here. The overhead is modest for all benchmarks for various cache size. There's only 1.1% degradation on average, and the worst case is only 23%.
Yeah, so going into now how this affects future control flow monitoring. So let's go over program shepherding first, which is basically just looking at the program and execution and finding control flow and then enforcing a security policy on that. So what are the flaws of this? Basically, it's built upon dynamic optimization infrastructure, which is basically just a software layer. So what comes with a software layer is just more space overhead and performance slowdown. So, and it also only allows code that was originally loaded, which means it cannot determine a source of data, especially because it requires intervention between every operation. So how does this solve this? Diff, the main thing you need to know is that it doesn't restrict control flow, but it does restrict the use of information. So what this means is that it provides source data for software layers, stuff such as program shepherding, but compared to something like hardware information flow, which restricts the flow of data, this doesn't do this, so it actually allows data to flow through. Yeah. Thank you.
Yeah, I got a question. So when they were talking about like the memory bandwidth overhead, and I think they mentioned like some cache overhead as well. Did they specify, like, did they look at a specific granularity for that? Because I'm assuming if it was like, if they were doing the tracking at the byte granularity, like the memory bandwidth overhead would be terrible, right?
So I believe they tested it at, they did test it at certain, I don't think they explicitly mentioned a specific bandwidth they tested it at. They just had the certain pollutions for different benchmarks that they had. So like for certain commands or certain tags, they would show the like what the command was and then the pollution for that. So.
Okay. Sounds good. Have none. Cool. Thanks, guys. Good job.
There's no more presentations today, right? It was just 3.
I think it's usually 3.
Okay, sounds good. Yeah, so I guess just look out for an email from the professor. But class is dismissed.
Thank you.
Good.